Well, hello everyone. It's a delight to be here. And yes, I am a kind of interloper. I recognise that. But there are generous helpings of narrative and science that I hope will make this talk interesting to you. I'd like to thank the organisers, of course, first of all, Nick, Robin, Anushka at SAMS, and also to the Carnegie Foundation who funded a lot of the work, including a Challenger website, which if you haven't seen it already, I'd invite you to look at. We digitally scanned the summary reports of Challenger with their thousands of data points, and we created a map which you can follow the journey of the Challenger and click on whatever station that they stopped at and see the species that they sampled, see the water temperatures that they recorded at the surface and at depth. So a very useful research tool, but also for the educators in the audience, sufficiently sort of accessible and interesting for a high school scientific module about ocean exploration. So I have a book in the offing. Its tentative title is Blue Wild, the Lost Marine World of HMS Challenger. And so the goal of the book, as with the website, is to bring the Challenger into the present, have 1 foot in the 19th century, but also 1 foot in the 21st century, a kind of split screen where a before and after, where Challenger's unique legacy is to have offered us a snapshot of the 1870s oceans by which we can compare the state of the oceans today. So what was the state of ocean science in 1872 when the naturalists of HMS Challenger set sail to plumb the ocean's unexplored depths? Well, the coasts of Europe and the eastern seaboard of the United States had been energetically trawled for specimens. American Matthew Morey had published an encyclopedia of ocean winds and currents based on the collective wisdom of old ship's logs. And the richly various marine phyla had been organised into something like their modern form. Now, Darwin's publication of The Origin of Species in 1859 had also given special impetus for exploration beyond the coastal shores of the UK and Britain. The deep sea, it was speculated, might harbour missing links between extinct life preserved in fossils and contemporary plants and animals. Now, for a half century before Challenger's epic voyage, so 50 years before 1870s, a loose network of marine scientists in Europe and the United States had been mostly shore-bound, rarely venturing beyond a quarter mile from shore to dredge up mussels and sea stars in co-opted fishing boats. Now, telegraph cables, a new deep-sea infrastructure, had awakened official interest in the ocean floor on both sides of the Atlantic. But to my mind, and this is very much arguable, it was a more nebulous set of circumstances. The Victorian fashion for all things marine, combined with the chance influence of a few well-connected scientists, including Wyville Thomson, that saw beach philosophising suddenly promoted in the imperial form of HMS Challenger to prestige science on the global stage. Challenger's scientific director, Wyville Thomson, he was a portly, bearded gentleman who would not have looked out of place on stage in a Gilbert and Sullivan operetta. But like many a repressed Victorian, he felt a deep affinity for beautiful objects. His tastes were unconventional, however. He was drawn to examples of animal elegance, the most remote from his own person. Nothing answered this criterion better than the deep-sea sponges, those sheer, bodiless relics of Cambrian times. Among the porifera, the glass sponges spoke particularly to Thomson's Platonic ideal of beauty. The genus Hyalonema, which has already been mentioned, sported threads of clear silica woven together in a coiling rope, crowned with glistening spun glass. The German naturalist Carl von Siebold had brought a specimen back from Asia to universal amazement. Nothing had been seen in the least like it before, Thomson wrote. The newly dubbed deep-sea Hexactinellidae, the glass sponges, spanned both time and space. Glassy imprints studded the chalk fossil beds of South England. But could the, quote, rich embedded lettering of the limestone be interpreted correctly without an intact modern counterpart for reference? On a foggy September morning in 1868 off the Faroe Islands, aboard HMS Lightning, which of course set out from Oban, Thompson had lucked upon a crowded bank of never-before-seen glass sponges. One emerged as a perfect gelatinous sphere with threads in a star pattern across its surface, and what Thompson described as a perfect maze of delicate glassy filaments for a base. Now, though delicate seeming, the sponge meshwork was unusually supple and strong, and he named it Holtenia carpenteri, after his dredging companion on HMS Lightning, William Carpenter. But a different genus, the Euplectella of the Philippines, represented the acme of glass sponge architecture in Victorian eyes. One species, Euplectella aspergillum, had earned the nickname Venus flower basket. Oh, here we are. Because its woven tubular form lured mating shrimp inside. The first Euplectella to arrive in Europe had been mistaken for an exquisite Chinese vase crafted by hand. I'm not kidding. By the time of Challenger's departure from England in December 1872, Thompson's desire for a living flower basket sponge had become almost an obsession, a circumstance well known to the ship's officers and the naturalists alike. The deep waters, go back to this map, the deep waters of Cebu Island in the Philippines, home of the Euplectella, had been circled on every map from the first day. Challenger's passage to the Philippines led them through some of the oldest European settlements in Asia and the most biodiverse seas on Earth. The archipelago hosts 3/4 of the world's corals and almost half of all known fish species. Strolling along the coralline beaches, the Challengers collected buckets of ornate shells, many with established market value among European collectors. In the equally lucrative sea sponge trade, the native Visayans held the advantage, at least for a time. Only the local fishermen knew the location of the precious Euplectella bank. When a European sponge seeker came to port, he was invariably pointed in the wrong direction. But the local monopoly hadn't lasted. When the waters in the Cebu Channel had first been harvested 10 years prior, in the 1860s, the rare glass sponges fetched the modern equivalent of $4,000 apiece. Now, with the Venus flower basket exhibited in museums and drawing rooms across Europe, you can guess what happened, the price had crashed to a little over $10. On a sticky morning in January 1875, 150 years ago, the scientists of HMS Challenger fulfilled at last their destined appointment with the glass sponge E. aspergillum. Thompson, accompanied by Henry Moseley and John Murray, set out early for a fishing village to the south. At the beach, flocks of curlews and graceful white egrets stood among the fishing boats. Here, Thompson enlisted 2 local guides for a pittance, with orders to bring them to the Euplectella. The first Euplectella aspergillum to reach England fell into the possession of the anatomist Richard Owen in 1841. He understood immediately the value of his prize, which he called, quote, the most singular and beautiful as well as the rarest of marine productions. Owen described for the Zoological Society of London a truly unique object, a skeletal lattice in the shape of a horn made up of shiny longitudinal, transverse and oblique fibres, quote, resembling the finest hairs of spun glass, winding spirally in opposite directions. Now, someone at the Society suggested that the shrimp, inhabitants of Euplectella, had built this fairy tale residence for themselves. He was roundly mocked for that opinion, even if no one else had a better explanation for how this wonder of nature had come to be. Now, Wyville Thompson, who saw Owen's Euplectella at the British Museum, contemplated the new order of glass sponges through the lens of deep time. The ventriculites of the English coast, tubular vase-like fossils with grooved decorations on their surface, had long confounded paleontologists. Now, here was a modern descendant to spotlight his pet theory of the continuity of the chalk. "We," said Thomson, "are still living in the Cretaceous period," he announced in the third ever issue of Nature, again to a general uproar. Now, Thomson's formal analysis of Euplectella would prove more enduring. It anticipates glass sponge research of the 21st century, carried out with electron microscopes and 3D printers. Thomson approached the task with caution because previous accounts had been riddled with errors. There seems to be something unusually fatal, he reflected, in the fascination of these beauties. First, he was surprised at the sponge's toughness, which belied its seeming fragility. Euplectella could withstand rigorous inspection and handling. His microscope, primitive as it was, disclosed keys to this resilience. Each glass fibre, called a spicule, contained a thin axial tube, ensuring suppleness and integrity. These individual glass threads were then cemented together in an elaborate curved lattice, like the interior or ceiling of a classical dome, the object of which must be to absorb the ceaseless buffeting of currents when fixed to the ocean floor, while still allowing nutrient-rich water to filter through it. The whole was an engineering marvel, a masterpiece of adaptation to the deep sea environment. For all the hundreds of Philippine glass sponges now in private hands in Europe, and the voluminous commentary upon them, a living Venus flower basket had yet to be properly described. So it was with a desire for this prize that Thomson, Moseley and Murray approached the Euplectella ground off the coast of Cebu. In the eyes of their Visayan guides, the sponge resembled the spout of a watering can, and they called it La Regadera. They had brought with them an ingenious trap made of bamboo, assembled in the shape of a Y, and armed with fish hooks. They led the Challenger scientists to an open area of water 3 miles offshore. Conditions were ideal. A full tide, smooth water with a strong undercurrent to manoeuvre them steadily across the quarter-mile-wide bank. The seafloor here was made of mud and sand, said the guides, with the base of Las Regaderas anchored in the soft sediment. Thomson and his colleagues watched the Visayans lower the dredge into the water on a thin hemp line to about 100 fathoms depth. After an hour's combing the seabed, they pulled the trawl gently to the surface. The moment it emerged was charged with excitement for the challengers, who counted 3 intact glass sponges attached to the dredge. With its perfect architecture honed by 500 million years of evolution, a glass sponge may live for a millennia until it is rudely extracted by a fishhook on a bamboo rod. On board, still alive, the Euplectella remained coated in a brown gelatinous slime, its living protoplasm. The silicate harness beneath felt rigid but flexible. On return to shore, the Visayan fishermen hung the sponges on a tree branch in the sun to bleach. After an hour, the protoplasmic casing dried and fell off, revealing the ornate skeleton that the Challenger scientists had journeyed thousands of miles to see. Thomson then examined for himself, at last, in the wild, the unique silicate design whose beauty, in Richard Owen's words, cannot be added to nor taken from. By day's end, they had brought washing baskets full of Euplectella back to the ship, purchased for 2 shillings a dozen. In his diary that evening, Challenger's junior scientist, Rudolf Wilhelm reflected on the expedition's banner day at Cebu. Quote, that Professor Thomson himself handled the sponges with the utmost care, freshly examining them all in all possible fluids as well, I need hardly mention. Despite their success, it seems the professor's ardour for the glass sponge was not yet satisfied. But when 3 days later Challenger returned to the very same spot in the Cebu Channel to trawl for more Euplectella, they got nothing. and within 2 years of their visit, the seabed of Cebu was completely barren of sponges. Euplectella, as per Gillen, continues to fascinate. A suite of research papers in the last decade has found that the Philippine glass sponge embodies resilient engineering at every level, from the laminated silica nanoparticles of its individual threads, which allow the stress spicules to crack without breaking, to the counterintuitive pattern of woven diagonal struts that skip every second square cell. Diagonal reinforcement of all cells would require more material for no advantage in strength. Because sponges, like humans, live in a world of strictly limited resources, evolution cherishes efficiency above all things. A 2019 experiment with 3D printing a Venus flower basket, in which it was allowed only the same material amounts as in nature, failed to replicate the sponge's resilience or its beauty. Industrial biomimicry of the Victorians' beloved Euplectella remains, quote, aspirational. The glass sponge fascinated Wyville Thomson with its inimitable beauty, but also its antiquity. In a public lecture in Glasgow he gave soon after Challenger's return, he speculated on the existence of charmed oceanic zones, the Faroe Islands, the coast of Portugal, the Philippines, which had by chance, according to him, been preserved through the geological upheavals that had transformed the rest of the planet, and it existed as de facto museum cabinets for strange and beautiful things from Earth's past. The Euplectella, for example, through some combination of luck and resilience, offered, quote, a glimpse of the edge of some unfamiliar world. Thomson's writings on the life of the ocean abyss are full of romanticisms of this kind. More's the shame, then, that Thomson did not live to properly share his exultant moment in the Philippines. On Challenger's return to England in May 1876, he confessed that, quote, the strain of the voyage, both mental and physical, was long and severe, and it has told a good deal upon all of us. Now, if we allow for Victorian understatement, I think that's a pretty strong declaration. 4 years later, he was dead, buried by overwork, with his essay on the glass sponges unwritten. Now you see what I'm doing here, which is to, through the eyes of Challenger scientists, to see the oceans as they were, a snapshot in the 1870s, but also to bring the story forward to the present. Now I want to shift to an experience in Australia recorded in Sydney Harbour by Henry Moseley. HMS Challenger steamed into view of the scenic sheltered bays of Sydney Harbour on Easter Monday 1874. The shore near the present-day Opera House was filled with colourful picnickers who swarmed aboard. Days later, the stream of nosy visitors had not abated. The Challengers, seeking relief, fanned out across the famous harbour with its countless creeks and coves overhung by eucalypts, a naturalist's paradise. Henry Moseley felt in particular an invitation to explore Sydney's abundant oyster beds. He rode one morning along a high sandstone plateau studded with the homesteads of the colonial elite before coming to a narrow chasm. He clambered down through a forest of luxuriant ferns with lyre birds in a bell-like chorus around him. At the bottom, he emerged from a gully onto the slippery banks of Barowra Creek, a broad, meandering tributary of the Hawkesbury River. Here, full 20 miles from the Pacific Ocean, marine life abounded. On a shallow sandbank, he observed stingrays basking in the sun. Nearby, a shoal of saltwater mullet sought refuge from a pursuing dolphin. He caught several of the grey fish with a single dip of his net. Then a swarm of jellyfish drifted by. He wrote in his diary that one might, quote, sit on a gum tree and fish for sharks. In this magical spot, it was impossible to tell where the sea ended and the river began. The molluscs of Barowra Creek in particular caught Moseley's attention. The rocks studding the creek bank were smothered with clumps of oysters, while large heaps of discarded shells lined the bank. At every juncture of a little creek or inlet with the main river loomed a vast shell midden. the legacy of 1 million meals consumed by the Gadigal community, who had inhabited this place seasonally for millennia, but had been recently uprooted. Now, for Moseley, who had ambitions to publish a popular account of his naturalist travels in the style of Darwin's Beagle memoir, the middens were an exciting find. Darwin's friend John Lubbock, he's the archaeologist who invented the categories of the Neolithic and the Paleolithic. John Lubbock had recently published on the shell middens of the ancient peoples of the Baltic coast. Here, before Moseley's very eyes, was the work of their Australian counterparts, shellfish architects of the Antipodes. In a cave above the creek, Moseley found more shell middens, but also wall paintings the Gadigal had left behind on their forced removal. A kangaroo, a fish, and then, by a more recent hand, a menacing stick figure in tailcoat and top hat. Contemplating these, even Henry Moseley, his mind tainted by Victorian prejudices, experienced a spasm of regret at the European invasion of this coast a century before, that had violently displaced a people so, in his words, interesting and original. The only Indigenous men and women he would meet on his Australian tour were detained miles inland on a reservation. There they were denied the opportunity to provide for their own subsistence, including all delicious oyster harvests, and forced instead to tend the cattle and crops of white men. The official narrative of Challenger's Sydney sojourn describes a magnificent haul of bivalves dredged from Sydney Harbour. A bridgeway between the northern tropics and southern temperate zone, the harbour possesses the full range of mollusk-friendly habitats: sandy beaches, sheltered rocky shores, mangroves, marshes, mudflats and quiet estuaries in the style of Barowra Creek. All across the harbour's nooks and byways, the ocean tides mix with fresh water from 1,000 rivers, streams and subterranean springs bubbling up through the porous soil. A bivalve heaven. This wondrous ecosystem, a product of the last glacial retreat, made the business of collecting molluscs almost indecently easy. More than 50 species lined the shelves of Challenger's workroom, some of them cosmopolitan types, but most wholly new and indigenous to the Australian coast. What Challenger's success with their rich bivalve collection obscured, however, was the imminent collapse of the oyster industry in Sydney Harbour. In 1770, Captain Cook had found Botany Bay flush with oysters, and shellfish had been a mainstay of the colonial diet in the century since. Oyster bars were popular accordingly, but the principal economic interest in oysters lay in construction. Shells by the millions were burned in kilns for lime to produce cement, plaster and whitewash, all necessary materials for a booming frontier colonial town. The most historically notable mollusk of Challenger's collection was the so-called hairy mussel, Trichomia hirsuta. Trichomia dominated the shell middens Henry Moseley stumbled across on Barowra Creek, though these were a mere fraction of their original size. The Trichomia mussels that the Gadigal people had dined on and accumulated over millennia, local lime kilns had decimated in little more than a decade. Looting the shell middens, though, had been insufficient to satisfy demand in Sydney, which entailed live oyster dredging, a form of coastal strip mining which commenced in Sydney Harbour in the 1860s, extracting hundreds of tonnes of shellfish annually from the harbour and surrounding estuaries. The crude dredge most commonly used was a heavy iron bar with a mesh bag attached, which ripped up entire reefs, and with them the C4 substrate that the molluscs relied on to reproduce. On shore, meanwhile, the clearance of forests for roads, houses and farms dried up nearby freshwater ponds and delivered tonnes of silted runoff into the harbour, choking the water column. In a critical development, the increasingly turbid waters of the estuarine harbour attracted an invasive mudworm from New Zealand, the Polydora. The tiny parasite took up residence with the oyster in a tube of mud, effectively suffocating it. A diseased oyster was instantly recognised by the telltale blisters covering the inside of its shell. Stillborn shellfish perished in their millions, including entire populations of trichomia. Soon afterwards, in 1886, mudworm disease struck the Hawkesbury River, struck the mussel population of the Hawkesbury. A generation prior, oysters had been harvested at the rate of 100 bags a day on the river. A decade after Henry Moseley's day trip, no shellfish remained. Already by the time of Challenger's visit, the alarm had sounded over the rampant destruction of Sydney's oyster reefs. A Parliamentary Act of 1868, the first regulation ever applied to a Southern Hemisphere fishery, vowed to curb, quote, the criminality of this shameful waste, but to no avail. 2 years after Challenger's departure, a royal commission was still lamenting the ruinous decline of molluscan beds up and down the coast, which have never recovered to their pre-colonial state. Now, this is true of temperate oyster-friendly estuaries across the world, such as the Hudson River and the Chesapeake Bay in the northeastern United States. Today, more than 85% of shellfish reefs are functionally extinct. Agriculture, not nature, produces oysters for the modern dinner table. Now, popular ignorance of this fact is an example of shifting baseline syndrome or generational amnesia, whereby the existence of entire healthy ecosystems, once destroyed, can be universally forgotten in a matter of years. Here's an interesting early illustration. As early as the public debates of the 1890s in colonial Sydney, quote, the question arose as to what a natural oyster bed was. 4 months after their Sydney visit, the Challenger arrived in Cape York, in northern Australia, where they observed the Indigenous residents harvesting mussels from the beachside shallows. A century later, so 1970, an anthropologist named Betty Meehan spent a year with the Gidjingali people on the nearby shores of the Arafura Sea, where the naturally self-replenishing oyster population continued to sustain more than a dozen families. Many of the bivalve species Challenger collected were still flourishing in Arnhem Land, according to Meehan's 1970s account, including trichomia. In coastal regions free of a colonial footprint, Australia's oyster reefs endured until climate change. Now, it's possible the decimation of coastal oyster beds in the days of HMS Challenger undermined the long-term resilience of the keystone kelp forests of the Australian east coast, which are now wilting from warmer ocean temperatures. In her winter crossing of the Tasman Sea in 1874 to New Zealand, Challenger's bow sliced through thick ribbons of seaweed on the ocean surface. A century and a half later, that kelp has mostly disappeared. Into this vacuum created by the kelp crisis, an invader from the north has seized the opportunity for territorial expansion, migrating south at the rate of 160 kilometres a decade. Cetrostephanus rogersi, a rapacious sea urchin with the ability to catastrophically overgraze seaweed beds, has transformed the ancient kelp-rich coastal reefs of the eastern seaboard of Australia into so-called barrens. An unrecognisable ecosystem characterised by impoverished reefs, invasive tropical species, and drastically lowered diversity. This potentially includes a multitude of mollusk species. Historically, Southeast Australia boasts one of the richest mollusk populations in the world. Trichomia and 1,000 others radiated outward from tropical seas over tens of millions of years. Geographical isolation since the final breakup of the supercontinent Pangaea and the creation of the polar oceans means that 95% of Australian mollusk species are endemic. Today, however, along a superheated Australian east coast, the hairy mussels and their kin are rapidly disappearing from view, to be interred with their forebears in the vast midden heap of extirpated life, terrestrial and marine, future fossils in the inglorious landfill of the sixth extinction. Now, John Murray. Let's wind back to Challenger's momentous first crossing of the Atlantic in the spring of 1873. While Professor Thompson, Moseley and Willem Soom spent long evenings aboard Challenger dissecting the larger charismatic animals from the dredge, John Murray concentrated his energies on the microscopic protists of the mud itself. What swam? What sank? He wondered. What of the graveyard of shells lining the ocean floor, yards deep? Did these animalcule legions live and die unseen in the dark parental mud, or did they sport miles above at the sunlit surface and descend only at death in a thick microbial mist, bodies dissolving en route, their vacant shells adding layer on layer to the ever-deepening strata of deep-sea ooze? We know the answer to that question. They were not sure. Every other evening at sea, the dredging platform of HMS Challenger stood feet deep in a deposit of freezing muck, like so much sago pudding. At which point Murray and the others waded in, little spades in hand, to shovel the ooze from one sieve into another, each finer than the last, until the tiny shells that lined the ocean bottom were separated from the sediment that entombed them. The life histories of these abundant shells and the single-celled protists they housed were controversial aboard Challenger. Wyville Thompson, a man partial to establishment opinion, believed them lifelong residents of the deep sea. Murray, however, once Challenger was far out from the European coast, discovered live microorganisms in the tow net he used to skim the ocean's teeming surface. One memorable morning, he dipped a teaspoon over the side of his small boat and was stunned to observe a living Globigerina floating there in all its glory, its protoplasmic body bursting out of its shell. In warmer waters, there it is, the Globigerina. In warmer waters, as Challenger headed south, Murray found that washing his tow net in a glass vessel left a residue of Globigerina and other ubiquitous foraminifera at the bottom. Under the microscope, he observed the fleshly orange-yellow protoplasm of the ever-present Globigerina boloides exude from pores in its spiral shell. From there, the oozy body spread out itself among the forest of spines that protected the whole, or were perhaps a flotation device, he thought. Later, as Challenger cruised over the abyssal waters of the mid-Atlantic, Murray continued to collect living Globigerina from the surface while their calcite shells vanished mysteriously from the ooze. The dredge in these deepest regions delivered up only an enigmatic red clay, devoid of life. Murray and Thompson were now equally baffled. Whether the foraminifera inhabited the surface of the ocean floor, whether they inhabited the surface or the ocean floor, why did one haul of the dredge deliver a crate's worth of shells onto the deck and the next day none at all? Then further novelties. Leaning over the side, Murray watched the ship's prow cleave great smeary chains of protists on the surface. He had the boat lowered to bring back more jars full of tiny spinning spheres to the laboratory. Under the microscope, he detected dozens of new radiolarian species, an alien patisserie of cones, frills, and lattice meshes to be stained with carmine and carefully mounted in balsam for future study. These radiolaria impressed Murray with their sheer evolutionary difference. In their captive jars, the radiolaria appeared wild and inhuman. Between a protist cell and the naturalist who peered at it via the length of a microscope opened a gulf of existence deeper than any ocean. Time, the great agent of radiolarian variety, assured their universal presence in the world's oceans. For hours at a stretch, in an open boat with the sun beating down, Murray followed the protistan streams as they drifted with the Atlantic current, a grand passive migration. Back on deck at night, he saw millions of them still, lit up in a sinuous, shining layer across the ocean's surface. Everywhere on Challenger's world-girdling voyage, whether he cut into the belly of a crab or a worm, a fish or an octopus, he found radiolaria bobbing there, staple food for ocean life. This meant radiolaria were ubiquitous, not only across the ocean surface, but vertically in the water column, to be gorged upon by marine animals of all neighbourhoods and appetites. The very month Challenger completed her first Atlantic transit, in March 1873, the German scientist Christian Ehrenberg published his pioneering study of radiolaria in the fossil record, what he called microgeology. Ehrenberg based his study on the radiolarian cliffs of Barbados. The island was a coral patchwork of ancient ocean beds uplifted from depths below the threshold, where carbonate shells dissolved. The inescapable conclusion? The freezing ooze Challenger had dredged from miles beneath the surface of the ocean would, in some future age, be transformed into a beach or forest floor, baking beneath a tropical sun just like Barbados. How this epic reversal of marine and terrestrial words occurred, as it must often have done, John Murray could not imagine. Ooze signified life, red clay meant death or the absence of life. The great plankton colonies at play on the sea surface flirted with the deep, floating and sinking by turns before their downwards mortal transit. Some were eaten as they descended by the sea dwellers lurking beneath the surface, while survivors reached their limits of acidic tolerance and dissolved. The calcite compensation depth, another Challenger first. For thousands of miles across the open Atlantic, this accounted for the entire protestant multitude, where the dredge scooped only lifeless red clay. Then, as they drew nearer to their Caribbean island harbour, the shell-studded ooze returns. There's a final twist in the tale. There's the radiolaria. There's a final twist in the tale also. In 2018, curators at the Natural History Museum, whose generosity I should take the opportunity to thank, they dusted off John Murray's foraminifera shells from Challenger plankton toes and set them alongside their 21st century counterparts exposed to elevated ocean acidity. Results were alarming. The foram shells of the Anthropocene were significantly thinner than Murray's pre-industrial baseline specimens. Corroborating research shows that the foram species now accumulating on the ocean floor are more fragile than those buried beneath them. The sea floors HMS Challenger cruised over 150 years ago are not our ocean floors. As this audience well knows, rising acidity in the seas, a direct product of runaway carbon emissions, threatens the viability not only of worldwide foraminifera populations, but all calcite shell-producing creatures, including mollusks, corals, crustaceans. The near daily spectacle of John Murray and his colleagues wallowing in Globigerina ooze, sifting for tiny shells, amused the foremast hands of HMS Challenger back in the last days of sail. But even then, Murray understood the importance of single-celled marine life to ocean history, from its ubiquity in sedimentary rocks from the Italian Alps to the West Indies. Hence the diligence with which he documented the extraordinary variety of these open ocean protists, while keeping close account also of the delicate seawater chemistry that, altered even slightly, will surely eliminate them from the fossil record of the future. Now, the concluding section, Challenger's legacy and a spat with Darwin. Challenger's object was always the deep sea and its mysteries. On their return to England in the spring of 1876, Wyville Thomson promised publication of the expedition's results within 5 years. In the end, full publication would require 2 full decades. By 1880, not a single volume had appeared. Questions were raised in the Parliament and the press by those who did not appreciate the complexity of the task. Almost 6,000 Challenger specimens in glass bottles, tubes and jars had been sent all over Europe and to the United States, a process which itself took several years. The writing of reports was then in the hands of specialists whose work schedules Thomson could not control, sound familiar, and with whom he was in infrequent contact. He had no Teams meetings, no texts. Correspondence on a single question might take months. And the inclusion of hundreds of illustrated plates, a spectacular visual legacy of the expedition, only added to the time and expense. Now, by 1878, 2 years after the return, early reports had begun to trickle in from experts in London, Edinburgh, Berlin. But because submission deadlines were non-existent, their subject matter was wildly variegated. And if you've ever edited a journal or an issue of a journal, you can sympathise. So the subject matter of the first pieces was wildly variegated, even hodgepodge. There were essays on brachiopods, sea pans, sea shrimp, alongside analyses of whale bones and even the green turtle fetus. Now, given the public's long wait for the Challenger reports and to avoid any sense of anticlimax in the debut volume's publication, Thomson decided to include a preliminary overview of the expedition's results. As a gifted, and I feel that Thomson came into his own here, as a gifted systems thinker in the Victorian style, he was ideally suited to the task of an expedition manifesto. Thomson's general introduction to Volume 1 of the expedition's scientific reports is a fascinating document because it distills what, to Challenger's scientific director, their principal aims and achievements had been. His focus on abyssal ocean conditions and the long-term evolution of deep-sea fauna is therefore telling. For a Victorian scientist with a sketchy understanding of geological time and a total ignorance of tectonics, Thomson's general introduction offers a remarkably lucid, mostly accurate theory of the oceans. His key categorical distinction in the essays between the familiar fauna of the seashore and the alien forms of the abyss, the glass sponges, the crinoids, the blind crustacea, and the grotesque fish species found worldwide by Challenger. The uniformity of deep-sea life was the expedition's principal finding, which Thomson attributes to the work of polar bottom currents issuing from the north and south, thus creating a stable temperature environment for marine life. Temperature, as Thomson states in his second general principle, is the supreme condition which determines the distribution of marine animals. Thomson's stated reasons for the differences between shallow and deep-sea fauna were more speculative and fodder for the ongoing bitter controversy over evolutionary theory 2 decades after the publication of The Origin of Species. Thomson surmised correctly that marine life had originally migrated from the shallows to the deep sea. The present differences between coastal and deep-sea life forms he attributed to the constant changes in geomorphology and sea level along the continental shelves, in contrast with a stable deep sea unchanged since Earth's formation. And we now know, of course, this was Thomson's most profound error in the light of tectonics. So far, so uncontroversial for 1880. In his essay's conclusion, however, Thomson finally committed himself to the fray as a Darwin skeptic. The affinity of the abyssal creatures collected by Challenger, sea lilies, glass sponges, with fossil relics of the ocean past, offered, quote, powerful support of the doctrine of evolution. But he could find no evidence for natural selection as the mechanism for biological change. Among Challenger's vast deep-sea collections, Thomson saw no, quote, insensible gradations from one species into another, no transition forms. There is, he concluded, and this is the fatal phrase, no difficulty in telling what a thing is. Now, Thomson's final throwaway line provoked a rare public attack from Charles Darwin himself. From its outset, the Challenger expedition had been viewed by the scientific community as an opportunity to prove or disprove Darwinian theory once and for all. If evolution were true, the deep sea would deliver a trove of living fossils visibly connecting ancient and modern life forms. Now, in the first public statement on Challenger's findings, its scientific director denied any such proofs had been found. Deep sea fauna was the product of, quote, progressive change over eons, said Thomson. But this slow and continuous process was due to slightly varying circumstances in the ocean environment, of whose laws, he says, we have not as yet the remotest knowledge. Now, for Darwin, the potential harm of Thomson's arguments to public confidence in evolutionary theory was serious enough for him to consult immediately with his most trusted advocate at the Royal Society, Thomas Huxley. As their first attempt at damage control, Huxley penned a careful review of the debut Challenger volume in Nature. He first praised Thomson and his scientific staff as, quote, the best equipped voyagers who ever left the shores of England for the purpose of enlarging the bounds of natural knowledge, end quote, and generously excused their delays in publication. On the lightning rod issue of natural selection, however, he both criticised Thomson's opinion as, quote, hardly so cogent as might be desirable, while also arguing that his main point, that transitional forms are rare and unusual, was in fact perfectly consistent with Darwinian theory. But Darwin, so that's Huxley, Darwin was not satisfied with this polite exchange of views. The day after his Friends review appeared, he enclosed in a letter to Huxley a more pointed rebuttal with directions to edit it and forward it to the editor at Nature. He was both enraged at Thompson and worried that any public expression of anger from him would undermine his hard-won aura of Olympian remove from public debate over his theory. If my manuscript appears too contemptuous, too spiteful, or too anything, he wrote to Huxley, I earnestly beseech you to throw it in the fire. In the letter rushed into print the following week in Nature, Darwin mocks Thompson for, quote, not understanding the principle of natural selection, and insists on his own full recognition of, this is Darwin, the direct action of external conditions on organisms. Now, the most heated section of the draft letter sent to Huxley, in which Darwin excoriates Thompson as, quote, a man who talks about what he does not in the least understand, Huxley quietly deleted from the published version. The letter is still, in his son and editor Francis Darwin's estimation, the strongest language Darwin ever allowed himself in print. A measure of the perceived high stakes of the Challenger reports to the public reputation of Darwin's theory. The Darwin-Thompson quarrel in the pages of Nature in 1880 might appear a footnote to the epic battle over evolution, were it not for the fact that of the decades-long eclipse of Darwinism in scientific circles in the wake of the Challenger reports, and that the basic terms of their disagreement have been recently revived. Current evolutionists have deployed the figures of the Red Queen and Court Jester to distinguish between two rival theories of species change. The first, classically Darwinian model, it emphasises biotic factors, notably competition, that's the Red Queen, while the latter invokes environmental perturbations such as climate change as evolution's principal engine, the Court Jester. In light of this, Thompson's general introduction to the Challenger reports stands as a seminal early contribution to the Court Jester school of Darwinism. Notwithstanding the intervening scientific revolutions, genetics and tectonics, the tension between the basic positions outlined in the 1880 Darwin-Thompson debate persists as an original fault line in evolutionary thought. On Challenger's return, the government predictably strangled funding for publishing its results before they were remotely done. Then Wyville Thompson died. At that dire juncture, the entire effort might have collapsed under its own weight, but for the intervention of an obscure young person Thompson had recruited at the last minute, John Murray. In addition to his magnificent administrative skills, Murray helped fund long-term staff and resources at Challenger House on Queen Street in Edinburgh, which churned out groundbreaking research reports for 2 full decades. Thompson's brave new ecology of the oceans shaped Challenger's research program and is a principal reason the expedition looms large to us in the age of dramatic ocean deterioration. For Darwin, species evolution occurred in a non-directional world, the uniformitarian model of natural cycles inspired by Charles Lyell. For Wyville Thompson in his Challenger school, by contrast, evolution takes place in a directional world of changing environmental conditions. Of the two, Thompson's philosophy is more directly applicable to our current ocean, the ocean of the Anthropocene. We inhabit in the 21st century a directional world, driven by ocean warming, acidification and pollution, not a pure Darwinian biosphere where natural selection operates against a backdrop of stable conditions. With Wyville Thompson at their head, the scientists of HMS Challenger, overworked and underappreciated, are sailing into their moments. And I'll leave you with the beautiful Challenger windows at St Andrew's Church in Linlithgow, where Wyville Thompson is buried. It's not a very convincing representation of the ship itself, but it surely captures the Arthurian spirit of the voyage, and it's definitely worth a visit. Thank you.